Good evening and welcome to this new Stay at Home episode of Astronomy on Tap London. Thank you for tuning in, and I'm hosting the event with Ayush today. Hi Ayush, and thank you for being with us. So we're going to talk about the laws of physics and that we use to explain the world around us and that are assumed to apply to every location and instant in the universe, but this may not be true. And I hope you're ready to challenge your certainties with our speaker and find out what connections this could have with some of the mysteries of our universe. So before introducing our guest, I would like to remind you that we'll have a Q&A session after the talk. So please post your questions in the YouTube chat. And also don't forget to subscribe to our YouTube channel and to follow us on our social media here to keep up to date with the next events. And let's now welcome Dr. Dinko Milakovic. Hi, Dinko. Thank you for accepting our invitation and for being with us tonight.
Hello, everyone. Hello, Chiara. It's nice to be here.
Yeah, so Dinko has recently started a fellowship at the Astronomical Observatory of Trieste after completing his PhD at the European Southern Observatory in Munich. It's where we met the first time. And actually, Dinko, we started our PhD the same day. So lovely memories. So apart from doing exciting research in cosmology, and we'll hear about it in a moment, Dinko has also impressive cooking skills, and he organizes fantastic dinners for his friends. And I can say it because it's based on personal experience. So I really recommend being among Dinko's friends. So Dinko, we could define you probably a gastronomer, so with the G in parentheses when needed. So it's both an astronomer and a gastronomer. So I wanted to ask you what started first, like your passion for cooking or for astronomy?
Well, I joined an astronomy group at my elementary school when I was around 8, but I would say my first passion was eating and then later cooking before a passion in astronomy, but quite close together in time.
Nice. Well, okay, so you're bringing that forward together, both cooking and astronomy.
Yes, that's true.
As you know, we post quizzes and little games on our social media before the event. And Ayush is going to summarize this week's questions for you. Feel free to post your guesses in the chat during this Dinko's talk, and we'll give the answers at the end. So Ayush, the screen is yours.
All right, thank you very much. So if you've been following us on our social medias, you already know what this week's questions are. So I'll just read them out very quickly. So the first question that we asked you is, which force of nature is the weakest? So I'm refraining from sharing my screen because that includes the answers. So you'll have to remember the choices, and feel free to put them in the YouTube chat box, or you can also head over to our Twitter, Facebook and Instagram accounts, and the questions are there already. So yeah, just to come back to the questions for this week, the first question we asked you was, which force of nature is the weakest out of all these? So the first option is gravitational force. The second option is electromagnetic force. The third option is weak nuclear force. And the fourth option is strong nuclear force. So gravitational force, electromagnetic force, weak nuclear force, and strong nuclear force. And you have to tell us which of these is the weakest. And the second question that we asked you this week was, the peculiar phenomenon causing the expansion of the universe to accelerate is called what? So your options for this question are, is it dark matter? Is it black pudding? Is it dark energy, or is it dark force? So which of these phenomena causes the universe, the accelerated expansion of the universe? Once again, is it dark matter, black pudding, dark energy, or dark force? So again, please start putting in your answers in the YouTube chat or on our social media, And we hope that these will be answered during Dinko's talk, and then we'll get you the correct answers at the end of this session.
Thank you, Ayush. Okay, so Dinko, feel free to start whenever you are ready.
All right, I'll start sharing my screen, and then in the case something doesn't work or you don't see anything, please let me know, and we can try and
yes,
make it work. So, thank you both Chiara and Ayash for a very nice introduction. I will be talking about laws of physics, and something that I find very interesting and what is a topic of my research: do the laws of physics vary? I will try to explain why it's, to me, an interesting question and why I'm so invested in looking for the answer to this question. I'll tell you something about what would be the implications, what is the current status of the field, and what are the prospects for the future. So we'll start by just introducing the laws of physics. For many of you, when you talk about laws of physics, the first association might be the Newton's law of motion, which basically just explains how forces and objects and the basic principles of motion. For those who are more inclined to electrical engineering, you might think of the Ohm's law, which relates voltages and currents. But generally, when we talk about laws of physics, we're talking about mathematical constructs which relate either different concepts or different measurables. So in the case of the Einstein's famous equation E = mc squared, it actually relates the concept of energy to the concept of mass. And some other formula here will relate forces to masses or charges with distances, time with velocity, and so on. And as physicists generally try to identify those mathematical constructions which are the most fundamental, those that explain the broadest range of phenomena all at the same time. So in principle, when we talk about laws of physics, we talk about two things. The first one is quantum mechanics. We use quantum mechanics to describe the behavior of subatomic particles. Subatomic particles go on to make up protons and neutrons, which make up the cores of atoms and nuclei. We talk about electrons, which together with protons and neutrons form atoms. Atoms form molecules. Molecules form everything around us. So quantum mechanics provides the mathematical framework in which we can explain many of the phenomena in our world. In this picture, you can see the image of a cloud chamber, and every blue line is a trace of a single subatomic particle. The second pillar on which we base our laws of physics is Einstein's general theory of relativity. It tells us how massive bodies bend space and time and how they interact, how massive bodies interact. So in this image, you can see a Hubble image of a galaxy which was lensed by two other galaxies that are located between that distant galaxy and us. So here you can see the effect of the gravitational lens, which we explained by Newton's gravitational theory. These two frameworks, general relativity and the standard model of particle physics based on quantum mechanics, form the framework in which we explain almost everything in the universe. Those are our fundamental physical laws. And we can actually explain a great deal just by using these two frameworks. Here you can see a graphical representation of the history of the universe. On the very left-hand side, you can see a representation of the Big Bang, how we think the universe was created. In this process, a large number of protons, neutrons, electrons were created, which went on to create hydrogen atoms and helium atoms, then which under gravitational interactions collapsed into first stars, and then stars started creating galaxies under the influence of gravity. And galaxies, again, form larger structures such as galaxy clusters. Inside galaxies, new stars created planets and ultimately us. So we can explain a great deal just by applying these mathematical constructs. And there is, however, one thing that we cannot explain, and that is a recent discovery that the expansion of the universe is accelerating. Before 1990s, astronomers expected that the expansion of the universe, and we know that the universe has been expanding since 1920s, the first observations by Edwin Hubble, we know that the universe has been expanding. So everyone kind of assumed that the energy of the expansion will drop and that the universe will be expanding at a slower and slower rate. However, in 1990s, measurements have demonstrated that this is not true, that the expansion of the universe is in fact accelerating. And this is something that was and is currently not explained by the laws of physics that we currently know. We can compensate for it. We can introduce a mathematical a lambda, for those who know what this means. You can introduce, you can explain it with mathematics, but you don't know what it is. We don't have a physical theory what is dark energy. So in this sense, dark energy is one of the greatest mysteries of contemporary science, not only astronomy, but also all of physics. Much research is actually devoted to understanding what could be causing this accelerating expansion, what is the physical cause for dark energy. And there are many surveys and astronomical research being done to understand what it is. Another approach would be to actually re-examine what we think we know about the laws of physics that we currently know. So I will talk about this for the next few slides. We have identified 4 forces of nature. Gravity, which is also the weakest of the 4. This answers one of the questions. We have the electromagnetic force. We have the weak and the strong nuclear forces. In everyday world, we will mostly experience gravitational force and the electromagnetic force. If you pick up your mug of tea, you would be counteracting gravitational force by applying electromagnetic force and everything else. So it's worth investigating these forces of nature to examine our hypothesis on how we think the universe works and try to see where things break down. There are also very interesting questions with these 4 forces of nature. For example, why are there 4 of them? Why not 5 or 3 or just 1? Why is gravity so weak compared to all the other forces? What sets the relative strengths? Why is gravity the weakest and not the strongest? And how all of this is seems to be fine-tuned for the existence of complex structures for stars to work, for galaxies, for planets, for life. And then it's also an interesting topic to an interesting question to ask if there are more particles and more forces that we are not aware of, and how they relate to the concepts of dark matter and dark energy. So we can examine these forces, and the easiest one to investigate actually is electromagnetic force. So I will be talking about this for the remainder of the talk. The electromagnetic force is characterized by a single number. We call it the fine structure constant, or alpha. It is defined, as you can see by this formula, where these numbers are the electron charge, the speed of light, and the Planck's constant. It is a number without units. It's a dimensionless fundamental constant with the value very close to 1/137. This number was not predicted by any theory. It is something we have to experimentally measure and then apply to all of our calculations in order for the calculations to agree with reality, what we actually measure. So nobody knows why this number has the value it does. And it might be that this value that we measure here on Earth is not the same what you would measure if you were located somewhere else in the universe, or if you measure it at a different time. So the assumption of all of our current physical theories is that this number is always the same everywhere in the universe and at all times. So investigating this might actually reveal something that we're missing in our current knowledge of the laws of physics. So the electromagnetic force will determine the strength of interactions between charged particles and light. This is something to have in mind as I go on. The value of alpha will therefore set some of the fundamental properties of atoms. In quantum mechanics, we know that electrons go around atomic nuclei in specific orbits. Every orbit has an energy, and these energies are quantized. You have to have specific energy values. Here they're represented by the red horizontal line. So the distance between the two horizontal red lines is proportional to the difference in energy. So closer lines means a smaller difference in energy, and more distant lines means a higher difference in energy levels. And for example, for an atom of magnesium, if an electron wants to jump from the lowest line in this figure on the left-hand side, it needs to the higher level, it needs to absorb light of a very specific wavelength. In this case, that would be 280.35 and 279.64 nanometers. And this is the universe as we know it. If the value of alpha was 5% smaller, this would change the distance between the energy levels in atoms. So in order for an electron to jump from a lower state into one of these two higher states would be also slightly different. You can see that the difference is on the first digit after the decimal point. If alpha is 5% smaller, this has great implications on the universe as we know it, because stars would not be able to produce carbon in the same way they do in our universe. And being carbon-based life forms, we would not exist. So we can measure the value of alpha by examining some of the properties of atoms and looking at the distances in their energy levels. And this can be done using spectroscopy. I will now just simply explain how we do it. Imagine you have a light bulb, and the light bulb emits a source of light at all wavelengths. That means that when you use an optical element to disperse the light into a rainbow, you would get a continuous spectrum where all the colors are equally present. However, if you look at this flashlight through a cloud of gas, the atoms in the gas would absorb light at specific wavelengths corresponding to the energy levels in atoms. And you would be seeing a series of dark lines at the locations where the atoms have absorbed the light. And if you look at it from the side, you would also see the re-emission of the same light as a bright line spectrum. So we would be concentrating on this continuous spectrum with dark lines. We want to measure the dark line positions. In astronomy, we do this by using quasars. Quasars are very distant objects which emit a lot of light and act as flashlights illuminating the gas in the distant universe. So by looking towards the quasars, we can actually examine the properties of atoms that are located between us and the quasar and learn something about the physics that happened at that time, because as we know, light has a finite speed. So it takes a long time for the light from the quasar to arrive to us. This video shows you how we do the observations. So the quasar would emit continuum light, seen here in the inset, and as the light went through this gas cloud, it left an imprint of dark lines. So we catch this light with our telescopes. We disperse it and we get the spectrum of a quasar. This is a typical quasar spectrum. We're not really concerned with what the peaks in this spectrum is. We are interested in the narrow absorption line, so the dips in the spectrum. These are the locations of the dark lines in our spectrum. The vertical gray lines show you the positions of certain atomic transitions, that is the energy levels in atoms measured in laboratories on Earth. So we want to see if the locations some time ago or in some other region of the universe is the same as what we measure on Earth. So I will now show a small video explaining how the influence of alpha on the positions of these narrow absorption lines. In the center of the figure, you can see delta alpha over alpha, which is the fractional change in the value of the fine structure constant. And as it changes, you can see that the lines move either to the left or to the right, depending on their sensitivity to the change in alpha. You can also see that the iron transitions located on the right-hand side, around 6,500 angstroms, move in the opposite direction of the iron transition, which is at around 4,300 angstroms, so on the left-hand side. On the other hand, silicon and magnesium lines do not shift very much, which allows us to constrain the value of alpha by looking at how different lines move with respect to each other, and then comparing this also with laboratory measurements. And this was done for a large sample of quasars in 2012 by a group of astronomers in Australia. This plot shows you their results. They have used 154 quasars or clouds seen by the Very Large Telescope, which is located in Chile. And they have combined this with 141 measurements made by the Keck telescope, which is located on Hawaii. So the two telescopes actually observe slightly different areas of the sky. And here, every dot, triangle, and square tells you what their results are. It shows the location of one of the measurements. The color code will tell you whether they find the value of the fine structure constant to be slightly larger or slightly smaller. Larger values are blue and smaller values are in pink, red. And the gray stripe is the location of our galaxy. And the very interesting result that came out of this analysis is that both telescopes seem to indicate that there is a clustering of positive values on one side of the sky and negative values on the other side of the sky. So this is true when you use one sample from only one telescope, but also when you combine them. So it gives some credence to the validity of these results. And the authors claim that there is a preferential direction across the sky in which alpha moves from slightly smaller values to the value that it has on Earth to slightly higher values in the same direction. And there is only about 0.02% chance that this is a random occurrence by randomly assigning positions to the measurements on the sky. So this would be a very profound result if it's correct. It would prove that the laws of physics do not apply everywhere in the same way, which is one of the assumptions of Einstein's general theory of relativity. That would mean that we would have to re-examine our physical theories, that we would have to make a new theory of gravity that would allow for this. Also, there are theoretical frameworks which try to replace both the standard model of particle physics and general relativity. They're called theories of everything. They can assume a higher dimensional reality in which we only see 3 dimensions plus time. And some of them predict variations of this sort. So it's very interesting because they can also explain possibly dark energy and dark matter effects. There are also some other theories which just assume that there are other unknown forces in the universe and new particles which could also cause variations in the fine structure constant. However, we must be very careful because this is still very uncertain. There could be systematic effects. And in fact, one was specifically found after the results of this analysis that I've shown you before came out. So we really need to be certain that what we're trying to measure, what we're measuring, is real and not some kind of effect which can emulate this kind of a signal. This is a very, very tricky measurement because the positions of these dark lines we're trying to measure would only shift by several atoms of silicon on the detector. So this is a very, very precise measurement we're trying to make, and we really need to be certain that we're doing it correctly. That's why we would need new instrumentation and new methods to advance the field and to make new precise measurements. So I want to finish by showing you a video of exactly that. There is a telescope being built right now in the north of Chile, which has as one of its scientific goals to further the field of varying constants, to make new precise measurements of the fine specific constants and possibly constrain some of these dark energy fields. Thank you for watching.
Thank you, Dinko. That was a very interesting topic, and yeah, very exciting studies for the future. So yeah, thanks a lot. Okay, so we have already a few questions in the chat, but before that, if you can stop sharing, then we'll summarize the questions again and give the answers.
All right.
Thank you very much, Dinko. That trailer for the new telescope looks absolutely fantastic, and I can't wait when the movie is released. It's definitely going to be action-packed and answers so many of our questions. All right, so now we've come to the point where we actually tell you the correct answers to the questions. So let me go ahead and share the slides and click play. So hopefully by now you can see the question in all its glory in full screen. And I think this question was briefly answered in one of your slides. So let's see how many people caught it. So the first question was, which force of nature is the weakest out of all these four? And the options were gravitational force, electromagnetic force, weak nuclear force, or strong nuclear force. And the answer to this was gravitational force. And surprisingly, yeah, we got a lot of votes on our Twitter poll at least, and 72% of the people got it correct, which is great work. Some people also voted for electromagnetic force, which, so Dinko, how would these compare in terms of strengths, if you will?
So the exact numbers escape me, but I would say gravity is by far the weakest of the four forces.
Yeah,
and the exact number just escapes me at the moment. Let's say it this way. Somebody once explained that if you fall from a height of 1 kilometer, it takes the gravity to accelerate you to a certain velocity some time, a few seconds or 10 seconds, 20 seconds, 1 minute. It takes the electromagnetic force, which will apply once you touch the ground, just a millisecond to stop you.
So yeah, the difference between gravity and all the other forces is
right.
Quite remarkable. Okay, so let's move on to question 2 from this week. So the question we asked you was, the peculiar phenomenon causing the expansion of the universe to accelerate is called what? So dark matter, is it called black pudding, which is my favorite answer, I think, to this question. Is it called dark energy or is it dark force? Now on Twitter, there was a tie between black pudding and dark energy. But I don't know, what is the correct answer, Dinko?
Well, the correct answer is dark energy. I don't know if black pudding can actually cause the universe to accelerate.
I think there's definitely some variations of black pudding that will cause your stomach to accelerate, but I'm not sure about the universe. And yeah, congratulations to a few people in the YouTube chat as well who got this correct. So yeah, thank you everyone for voting, and we hope to get more of your participation in the quizzes that follow in the coming weeks. So back to you, Chiara.
Thank you, Ayush. Okay, so we can now address the questions in the chat. So we had one right after you started your talk, Dinko. So is gravity actually a force? And what is a force?
Right. So is gravity actually a force? In a strict sense, no. There is a famous quote, I forgot, it could be Einstein, but I'm not certain, that mass tells space how to bend and the space tells mass how to move. So it's an interplay of things. And in strict sense, gravity is not the force because it's not mediated by a force carrier. For example, in electromagnetism, the force carriers are photons, and there is a similar carrier for both the strong and the weak nuclear force. And people would say that there is no graviton, a theoretical particle which would mediate gravitational force, therefore gravity is not a force. But then again, we know that, let's say, quantum mechanics and the theory of relativity are incompatible, and there will be a quantum gravity theory at one point.
Thank you, Dinko. Okay, so Ayush, would you like to take the second question?
Yes, so just reading from the chat here, the second question is, how can strong nuclear force be the strongest when its influence can hardly leave the nucleus?
The strength of the forces is expressed in terms, again, of mathematical constructs. And in the mathematical equations, you have numbers, such as the fine structure constant for electromagnetism. You have a coupling constant for the strong nuclear force. And that is what we use to, let's say, rank the strength of the forces. So even though the influence of the strong nuclear force is very limited, its coupling constant is very large and is the largest of all the four.
Okay, so let's go to the next question. What will happen if, for some reason, the fine structure constant gets increased or decreased a little bit today? Will the existing carbon atoms be destroyed, since you made the example with the carbon atoms?
Right. So considering we exist, we know that the fine structure constant hasn't changed by this much since the beginning of the universe. And we can see quite distant into the universe, so we can constrain variations of the fine structure constant across this time. And current constraints, the ones I've shown you, but perhaps haven't really explicitly stated this, give constraints which are at the level of 10 to the minus 5. So if there was a change in the value of alpha, it must be smaller than 0.000 and then some number. So we don't know actually if it varies. Maybe we'll find at some point that it does vary, and with time it might get to the point where carbon atoms might not exist. But I think that won't happen in time soon, and we don't have to worry about disappearing out of existence.
That makes me feel safer,
yes.
Even with these variations found on the sky. Okay, so the next question concerns alpha's relation with redshift. Is there any relation with redshift?
Right, so the authors of the study I've cited do mention this, and they do compare models such as just a simple time variation versus simple spatial variation, and they find evidence for they do find evidence of a slight time variation in the fine structure constant. Although, as I've said, it is very tricky to actually say if there is such a variation. Measurements are still quite uncertain.
Yes, so I guess when the extremely large telescope will start observations, probably will be easier to give an answer thanks to the
Exactly.
more precise measurements. Thank you, Dinko. Okay, so we have another question. What is the difference between the accelerated expansion we have today and the inflation?
We think that the inflation was also a very quick expansion of the universe, but it was with a much higher acceleration than it is today. So during the inflation, we think that the universe increased by 10 to the third power of 30 in size in something that is much, much smaller than a second. So the current accelerated expansion of the universe is nowhere close to this. And it's not known whether the same physical, if it has the same physical source, if it has the same physical cause. Probably not. I think that's the consensus.
Yeah, but I think both of these things are so highly uncertain at this point. I mean, we know that these things happened, but why they happened or how they happened are still very, very open questions. So hopefully, in the future as well, we get closer to the answers. Okay, so finally, I think this is the last question from the chat. Why is the dark energy called energy?
That's a good question. Currently, people think that this is, well, there are two answers, or let's say two different ways of saying this. If you remember in Einstein's theory of relativity, in Einstein's equation E equals mc squared, we said that energy and mass are conceptually related. So we can express the equations governing the expansion of the universe, which Einstein also did. And then there is a certain term which consists of all the matter and energy in the universe. And we can have all the matter that forms stars, galaxies, us, and so on. We have a term for dark matter. And then there is a term for dark energy. So conceptually, they're all kind of, well, I won't say they're related. It's a completely different thing, but it can go in as an energy component. It's thought that this is actually vacuum energy coming from quantum fluctuations in the vacuum. But again, the calculations are off by 100 orders of magnitude with respect to the measured values. So again, something is wrong, and we know that there will be some corrections to our understanding of the laws of physics.
So in a way, dark matter sort of behaves at least gravitationally like matter would, but
Exactly.
Dark energy is sort of all pervasive, can be felt in every part of the universe,
exactly.
and
That's
sort
also
of like an invisible sort of energy that is dominating 76% of the universe now.
Exactly.
Yeah, blows your mind. Right, so I think, yeah, that's the end of the questions from the audience. Very, very interactive session. Over to you, Chiara.
Yeah, well, Dinko, it was a great talk, a very interesting topic, so keep going with your research. We have a request for a clarification. What do you mean 70%? Like maybe, Ayush, maybe you said 70? I don't remember now.
I'll let Dinko answer that.
What do you call this in English? Kicking the ball? No, so, if we make these, if we use Einstein's theory of relativity to explain the expansion of the universe, we would need to put in 76% of dark energy components mathematically in order to make the observations and theory agree. And there are other reasons also why we think that dark energy makes 76% of the universe. But let's say quickly that would be it. We need 76% of dark energy to make everything, the theory, fit observations. But it's very phenomenological. We don't have an explanation for it.
So to explain the workings of the universe in a way,
exactly.
Yeah.
Okay, so yeah, Dinko, thank you for being with us and for talking about your research. We will be back in 2 weeks with a different topic. And in the meantime, don't forget to subscribe to our YouTube channel and to follow us on our social media. Thank you for joining us.
Thank you, everybody.
Bye-bye.